So welcome back. I hope you had a lovely break time away from your computer. We're going to continue with our exploration of waves by talking about sound. So this week is going to be all about sound. What is sound? How do we describe it? What are its properties? And looking a little bit more at the math of waves as it applies to sound. So our first question is, what is sound? And what determines what type of sounds are produced? So I have a series of demonstrations that I'm going to do, then we'll look at some screencasts, and then we'll take some notes, and that'll be what the pattern will be for today. So what is sound? Well, hopefully what we remember, the things that we should know about sound right now, is that it is a mechanical, longitudinal wave. Mechanical meaning, that's right, that it needs material medium for transport, cannot go through a vacuum, and longitudinal meaning that the particles of the medium vibrate along the same direction or along the same axis as the direction of energy transfer. Now, how is sound different than what we've talked about? Sound is a three-dimensional wave as opposed to a two-dimensional wave or a one-dimensional wave. So we talked about waves along a string or a slinky. Then we talked about water waves, which are along the surface of the water, 2 dimensions. Now sound, so I make sound, it emanates out in all directions from the source. So with that being said, I'm going to do a demonstration and I want you to take note. And after the demonstration, I want you to make some observations and then we'll see if we come up with the same observation. So here we go. Ready? Listen. All right, pause the video and write down some observations about what you noticed. Okay, hopefully in your observations, you noticed a couple of things. One is that in different parts of the demonstration, you heard different sounds, but what was different about them? What was different about them was the pitch of the sounds. Pitch is a word in sound that means the same thing as frequency. So frequency means pitch, pitch means frequency. We wouldn't talk about the pitch of a light wave. You only talk about the pitch of a sound wave or pitch of a water wave. So it's a very specific vocabulary term to sound. So you should have heard different pitches. So in what ways were they different? Well, I think the next most basic thing that you should have observed was that when the bottle was at a specific water level, that whether I blew across the top of it or I tapped it, the pitch was different, right? And then the last thing I hope you notice is that depending on the amount of water that was in the bottle, the pitch was different. But something very specific you should have noticed. So here's what I'm going to do. I'm going to blow across the top, spill some water out, blow across the top, spill some water out. and until we get down to the bottom, and then I'm going to tap and add water in so we can see the next pattern. So listen, pouring water out. Hopefully what you heard there was, as there was less water in the bottle, the pitch, when I blew across the top of it, got lower, right? Deeper is another way people say it. Like this pitch here, it's a very low pitch. Now, in terms of tapping it though, no water in the bottle. Add water. Sorry, I gotta do this slowly so I don't make a mess. So add water. Pitch is going down. Add more water. Right? And add more water. There you go. So sort of weird in that sense that when I blew across the top, the more water that was in the bottle, the higher the pitch got. And when I tapped, the more water that was in the bottle, the lower the pitch got, right? So for all of this, we try and like bring it together and see if we can figure out something about what causes sound. Well, when was there sound in the first place? I was just sitting here, there's no sound, right? When I blow across the top, hit this, do whatever, or even use my vocal cords, I think the number one thing that you see in each case is that some mass is being disturbed, right? That's what causes sound. So sound occurs when mass vibrates, right? So vibrating mass causes sound. Nice and simple there. Now, what determines the way that that sound vibrates determines what the pitch is. So hopefully you see there are probably two factors then that determine the pitch of the sound. The first thing is, what is vibrating, right? That's the reason why blowing across the top and tapping the bottle produce different sounds. Even if it's the same thing, a different thing is vibrating. So what's vibrating in each case? Stop the video and take a guess. So hopefully what you figured out is when I blow across the top, what's vibrating in this case is the column of air that's inside the bottle. So from the top of the water line to the top, when I blow across the top, that air column vibrates. When I tap, what's vibrating here is not only the bottle, but also the water. And so knowing that is going to help us figure out something about our last set of patterns. So what determines the frequency of sound that's produced? Number one, the material that vibrates, right? Whether it was the air column or it was the water and the glass, right? Different pitches for different materials. The second is something about the amount of material that's vibrating. Remember, as I added water to the bottle, when I blew across the top, the pitch got higher, and when from tapping, the pitch got lower. Well, let's see what's happening. When I add water to the bottle, think about what's happening to the amount of the length of the air column, right? That air column is getting smaller and smaller and smaller as I add water, right? But simultaneously, the amount of water is getting greater, right? So with a small length of air column, I get a high pitch. If I pour some water out, I get a low pitch, right? Now, you may be tempted to say it's the volume of air, but it's actually going to be the length of the air. The thickness of that air column, the width of it, has a small factor in the frequency, but not as important as the length. It has what's called a secondary effect. The primary effect is about length. And when I added water here, what I'm doing is increasing the length of the water column. That's why I got a lower pitch. So there you go. Now that should be familiar because we've seen before somewhere where frequencies were inversely proportional to length. Where was that? And if you thought in the standing wave equation, F being NV over 2L, then you're correct. Because that's what's happening here, folks. Every time you hit an object or cause it to vibrate, all objects will naturally vibrate, if they're not forced to vibrate in a certain way, in a standing wave pattern. So it makes sense that that equation that we talked about is what's governing what's going on with the production of sound. So what have we learned here? We've learned that sound is caused by vibrating mass. We've learned that the stuff that's vibrating affects the pitch that's created, and the length of what's vibrating affects the pitch that's caused. Let me just verify a couple of those notions for you here. What I have here are a set of tuning forks, right? And so notice here, my tuning forks are all of different length. So let me just hold them up here for you, right? Which of these do you think, if I hit it, is going to make the highest pitch sound? All right, let's check. So here, going from this side to this side, listen. Pretty. It's that one. The shortest one made the highest pitch sound, and the longest one made the lowest pitch sound, which should not be surprising based on what we talked about with the bottle and the water. So now, just to show one last thing before we go to Screencastify land, I just want to show you that idea of vibrating matter. So I have my tuning fork. Now, I don't know if you can see it, but you see how when I hit it, it looks like the top edge is a little bit blurry. That's because the tines of the tuning fork, those are these, the sticks, right, of a fork are called tines, T-I-N-E-S, right, are vibrating back and forth so quickly that they create that blurring effect like the blades of a fan when they're moving, right? So here we go. But how quickly are they moving back and forth? Well, I'm not sure if you can see it on this tuning fork, but written right here is 512C. 512 meaning 512 hertz. What's a hertz? A hertz is a cycle per second. That means that each of these tines is moving back and forth 512 times per second. And it's going so fast that we really can't see it. So let me make it a little bit more obvious. Right, here we go. There you go, right? Hopefully you saw the water just shoot out in all directions as the tines of the tuning fork hit that, right? So there you go. Vibrating mass creates sound. Now, you may have also, just might as well do one more demo since I have everything out here. You may also have seen people play with wine glasses, right? And do this, right? Okay. Let's see if I can get this one. That one doesn't like to play, apparently. Nope. I guess we're not going to get more than just that one to do it. There we go. Ooh. Well, either way, you heard hopefully two different pitches here. Think to yourself, and I'll answer at the beginning of the next video, why did you hear two different pitches when I caused these two things to vibrate?